So greetings. This is our lecture for October 28th, 2013, and I'm going to talk about Montgomery algorithm in this video taped lecture. This particular algorithm is very useful in converting encryption algorithms or carrying those algorithms in binary arithmetic. As you would all recognize that our computers today all deal with binary operations, and in contrast, what the encryption algorithms primarily deal with modulus p operations, and in these operations, the modulus p is typically a prime or a prime power, and that makes the two fields of arithmetic incompatible. And so what Montgomery did, he succeeded in bridging the gap between the two by creating a transformation which makes encryption algorithms, their computations in binary, very efficient. So let us recall first of all the four basic operations of modulo arithmetic, and then we could actually see how, for example, when p is a prime or a prime power, what kind of a problem we could actually be confronted with. So if you take two operands u and v, as I've indicated over here, and add the two together and then compute it in mod p, then effectively you're doing this computation here, which is to say that you are computing the residue or the remainder of u plus v when it is divided by p. And so this can be simplified to this expression here on the right hand side. If u plus v is actually greater than p, then you take out the p portion of it, and that leaves out the remainder of u plus v mod p. If, on the other hand, it's not actually greater or equal to p, then whatever you added is exactly what you will get as the remainder of the sum of the two operands, mod p. In the event that you're subtracting v from u and then still want to compute mod p of it, that is the remainder of the difference, then again, by definition, that difference is formulated in this fashion here. And now we're looking at a difference divided by p, and this difference can potentially be as big as minus p or p minus 1 possibly, and could be negative because v could be actually greater than u. And if u is 0, it'll be minus v, in which case, of course, v could be as big as p minus 1. And so, you now have some number here that varies between, let's say, p minus 1 in negative terms and 0, and then divide that by p, so this actually leaves minus 1 in here. And so that minus 1 multiplied by this minus p will give you a plus p. That's what you see here. And that plus p is the correction step. If, in fact, the difference is greater or equal to 0 and less than p, then there's no need to make a correction. That means u actually itself is greater than v, and then you're subtracting one from the other, so the difference must be less than p itself, and therefore there's no need to correct in this case. Now, the last two expressions here handle a multiplication and division, as you see. Now, in these situations, since we are multiplying two operands, that each of which can be as big as nearly p, let's say, the maximum would be p minus 1. So you're talking about a number here that could actually go up to p minus 1 times p minus 1. So it would be basically then p minus 1 square. And that's pretty close to, let's say, p square. And so that means this quantity here could be as large as p. And if you do this in binary, then you actually need about log p iterations of division. And that is the problem. That is the problem in the sense that anytime you want to compute the remainder of a product of two operands mod p, you need to perform that division if you actually do this computation in binary. And the same goes for u times or u divided by v mod p. Now this division actually simply means that you are going to multiply u by the inverse of v, and that becomes a multiplication again. And that multiplication, of course, will now have to be modded to p, and that's the same computational complexity in terms of the number of steps involved in this division process. This ratio involves log p iterations of division, repeated subtraction. Now here I just simply mentioned that this number v inverse is that number which, when multiplied with v, then gives a remainder of 1. So you can actually move this one over to the other side. So you can see that the difference of the two, that is v times v minus 1, v superscript minus 1, minus 1 is equal to pz, some multiple of p, and that makes those two numbers, that's v times v superscript minus 1, minus 1, that is to say that the two numbers are congruent. V times v superscript minus 1 actually happens to be the same as 1 in mod p. And that's how we define this inverse. It's the multiplicative inverse, basically, of v with regards to mod p. So these are our 4 basic operations, and we need to do these operations repetitively and very frequently, let's say, when we're doing encryption computations, where our modulus p is some prime or prime power. Here I just laid out some examples. I guess these are the same examples in my lecture notes. So here's a prime number 53, and then we got 2 operands, both of which are less than 53, and we just want to add them up and mod them to p. So our first step would be to add them up, as we would normally do in binary, and that's our computers. That basically data path provides us this computation free of charge. And now we get this sum, which is 58 in this case, and that's greater than 53, so we got to do the subtraction being 58 minus 53. This is our mod, and that's how we define mod p in this case. And of course that is the same as adding the 2's complement of 53 in mod 64. This is binary addition still, keep in mind. And so this whole thing becomes equal to, or reduces to this addition over here. And we perform the addition, we actually get 5, which is what we would have gotten if we had subtracted 53 from 58. So all of these computations are going to take place in binary. This is not much of a problem because we could always perform one extra addition or subtraction. That's not going to complicate matters too much. What would complicate matters is when we actually have these multiplication and division operations, then the number of steps that we have to perform to get at the residue or the remainder of the product of the two operands, or the ratio of the 2 operands. That would be the log p number of operations. That's what we want to avoid by creating this transformation that Montgomery did. So subtraction is the same. When we subtract, let's say, 33 from 25, as we do over here, again, we just simply add the 2's complement of 33 to 25, and that becomes an addition one more time. And we get a number, in this case actually minus 8. So this is the one that we need to correct. In this case, the correction involves addition, as you just remember. We actually did show it over here. That's a plus p. So that's the plus p that you see here is just exactly what we're doing. When you do the addition, in mod 64 you get 45, and that becomes basically the result that we're interested in this case. Effectively, this again, this computation becomes a subtraction in binary, reduces to, and then a correction step. The 2 together will give us then this number 45 mod 53. That is, the difference of the 2 is actually equivalent to 45. That's the same as like saying this is equal to minus 8 mod 53. Since minus 8 minus 45 is a multiple of 53, these two numbers are essentially identical. Minus 8 and 45 are the same number in mod 53. Okay, so now if you just go ahead and do a multiplication, for example, this is what I was alluding to earlier, like multiply 25 by 33, then you get a large number. That large number could be like as big as 825. So this is the multiplication process. You have to do this regardless. But then, in order to know what this number is, mod 53, you have to deal with division that comes from this ratio here. This ratio has to be computed, and that requires division. Division is actually slower than multiplication. Multiplication can be carried out faster than division because division kind of requires prediction of sorts, that you have to guess what the quotient would be, whereas multiplication can be sort of like oblivious to that kind of a prediction. Just it's a repeated addition. All right, so given that fact, this 825 now needs to be divided by 53, and that gives us the the remainder in this situation. So you need this long division effectively. Here we have the product of the two operands, which we find out to be 825, and we want to compute this mod 53. That is equal to 30, but to know that it is equal to 30, we got to do this long division. When we do, we get a quotient over here and a remainder over down here. So that remainder is 30, and that we only can figure out by going through this long division. If in fact we hadn't found a way, as Montgomery actually did, we got to perform this sort of a long, tedious division process. Now, along the way, we also would actually be looking at numbers in this so-called congruence or equivalence relation fashion. Basically, when we look at numbers mod p, we are looking at numbers between, let's say, 0 and p minus 1. That's the mod that we have. And of course, there are lots of other numbers. There's, for example, p itself that is not in the notation. We only go from 0 to p minus 1, and so p happens to be 0, and so p plus 1 becomes 1, and p plus 2 becomes 2. That kind of thing. Now, so every one of those numbers outside 0 and outside of the interval 0 to p minus 1 kind of gets mapped to one of these numbers. That's what congruence is all about. So, most precisely, we say that two numbers u and v, and these need not be less than p. They're congruent, and we write this relationship in this fashion. And mod p, and sometimes we drop the parentheses, the pair, and we write it this way. If and only if the difference of the two numbers, it doesn't matter how you write this difference, whether you write it v minus u or u minus v, it is the same thing, is a multiple of p. That is, some number, some integer exists, which when multiplied by p actually gives you that difference. So for instance, 11 minus 5 is equal to 6, and that's a multiple of 6. So we can say that 11 and 5 are congruent. You could have also subtracted 11 from 5 and arrived at minus 6, and that also is a multiple of 6. And likewise, all these numbers like 2 and 4 and 6 are congruent mod 2 because they're all even numbers, and when you divide them by actually 2, you get 0. So they all map to 0, and they're all the same number. That's what congruence is all about. Now, congruence is an equivalence relation, meaning that every number is congruent to itself. And it's a symmetric relation, of course. That means if A is congruent to B, whatever mod you pick, B is then congruent to A. And finally, it is transitive, meaning that if A and B are congruent and B and C are congruent, then A and C are also congruent. So what that does, of course, is it takes all the numbers, all the integers, plus and minus, and then divide them into exactly P classes, equivalence classes. And these classes would then be denoted by 0, 1, 2, all the way up to P minus 1. Those are our equivalence classes under this congruence relationship. I just talked about this, so those are the classes we talked about. Now, there's one other thing that I have to maybe underline one more time. When we think about an inverse of an integer u mod p, we kind of like identify that with this multiplication being congruent to 1. So when I find a number, let's say, and I call this u inverse here, and multiply it by the number u itself, if there's such a number, that let's say that I find this number u inverse, there's some number like that, and I multiply it by u, and then actually that number minus 1 is a multiple of p, that's what this means anyways, congruence, then that means that that number, which I call u inverse anyway, is the inverse of u, whatever number that is. So it's sort of like important to have this, because with this relationship, we will be able to actually to perform multiplication operations under this congruence, and that will be handy in understanding the Montgomery algorithm. Now, there's also this other important fact that we're going to make use of, and that is this. If I pick a prime number, p, it doesn't really have to be a prime, but in the context that we're dealing, it suffices to pick that number p as a prime number. And then if I also have a positive integer r, then there exist two other numbers, which I will call v and z, such that r times v minus p times z is equal to 1, which actually makes this number v the inverse of r, basically, because rv becomes congruent to 1. That's because their difference would be multiple of p. Therefore, they are going to be congruent, and that's exactly how we define the inverse over here. If, in fact, that number, which we call the inverse of u, times u is congruent to 1, then they are inverses. So this is how that is written down here. Now, to show that this is the case, that is, in fact, this v is the inverse of r mod p, and don't forget that this number r itself can be actually larger than p. That doesn't matter, because every number is ultimately, under this congruence relationship which we just defined, will be mapped to one of those numbers between 0 and p minus 1, the integers, one of the integers. So the proof of this proceeds like this. Given that p is a prime, there must exist two integers v and t, such that r mod p times v minus pt is equal to 1. What this is really telling us is that this r mod p is in fact that number which is congruent to r, but actually represented as that number between 0 and p minus 1. There must be such a number. One of these numbers between 0 and p minus 1 must be that number. And since whatever number that is we come up with, this r mod p is some number between 0 and p minus 1, that number, except 0, of course, 0 does not have a multiplicative inverse, that number, when multiplied with some other number, and then from that we subtract some t multiple of p, that must be equal to 1. This really comes from a fact that we had established earlier, which had said to us that if p is a prime, every one of the numbers between 1 and p minus 1 must have an inverse, and that inverse was unique, if you recall. We proved this earlier in the semester, some 2, maybe 3 lectures ago. And so all this is saying is that, there is this number which we have to sort of assume, not assume, but in fact compute by taking that r and then just containing it between 1 and p minus 1. There is such a number, there's no question. This is because this number itself could be 1, 2, 3, 4, all the way up to p minus 1, which we don't really know. But it is the one that r is congruent to. And whatever number that is, then there must exist a v and a t where this difference is equal to 1. That is to say, this is the inverse. That thing is, this v is the inverse of this number. So now that we have that, we will just substitute this computation by its definition, and that would be just r minus r over p multiplied by p. That's how we define r mod p, and multiply that by v, which is that v over here, and then subtract this quantity, which we do, and then set it equal to 1. So this formula now reduces to this because we replace this by this. So all of a sudden now we have this equation, but then all we have to do is just isolate r times v, which we do, and then combine these terms together, which is like minus p times this whole thing times v. And now I've just realized that I need to put a v over there. So let's just see if I could actually add that v in there. It'll take a little bit of a time. Let me just go ahead and do that. Just quit out of there. So let's see if it opens up real quick. Good. That means I got to put this v over here. Close that. Okay. Now we have this formula. Everything sort of like checks out now. And this quantity here that we we have inside the parentheses here, we kind of call that number z. See right there. Whatever this is, this clearly is an integer because we have an integer here in the floor, and multiply that by v, that's another integer, and then plus t, that's another integer. So integers added together, we get an integer that we call z. So this whole formula now becomes r times v minus p times z equals 1. So this is the form which tells us that v is the inverse of r. I need to make one more correction here, which is that right there. So I also have to make this change here, right there. And now we get what we want, which is to say r times v is congruent to, or mod p is equal to 1. That's what this really is saying to us. Or v itself is congruent to r inverse. So we found we actually established this remark that when r is a relatively prime to p, or when p is a prime that actually happens by itself, then we get ourselves an inverse for that r, mod p. So to recap, if I pick an r, any r really, and then pick a prime, then r is always invertible with respect to mod p, and that gives us this number r inverse, which we call in this case v, because that's what the formula indicates here. So now that I've done that, what I'd like to show you that in fact we could use this, let's see, we could use this fact to make this transformation that Montgomery discovered earlier, where all of our mod p computations can be converted into mod r computations, where I can pick this r to be some power of 2, which in this case is 2 to the k, and I can place my p between 2 to the k minus 1 and 2 to the k. Remember, the r I picked in the earlier proof had no restriction on it. It's any number that I pick. As long as p is a prime, this inverse relationship applies. That is, that there is an inverse of r mod p. So this r equals 2 to the k is just like one such instance of r. And for this r as well, there is an inverse mod p, and that we call v. So now that is given, we actually are able to invert r, and that will be very, very critical in the computation of mod p arithmetic in binary. So, and here what we do is we actually define what's called the Montgomery pair of a positive integer, u, with respect to a prime modulus p, and that is given by this formula. So you can see that we take that number u and map it to a place, to another number, which is u times r mod p. So there is a transformation. We start out with the numbers from, let's say, 1 to p minus 1, and then we go to some number u times r, which is still modded to p, so if we kind of fall right back into the same place we began. This is important because as this transformation is put in place, let me just see if I can connect my power back in here. That way I know that my machine is going to behave right here. And in this transformation, I'll just show this in the next slide, that this transformation is actually one-to-one onto, which is critical. And so we also define what's called the inverse Montgomery pair of V as that number U, which this is, where V is multiplied by R inverse. So now we can actually go between the two. That is to say, U is actually equal to G inverse V. That is, it comes from V. But it is defined by this product, mod P. But V itself was actually equal to UR, mod P, over here. And now we multiply that R inverse mod P. And we can actually take this R inside. And then R times R inverse will actually give us 1. So now, and then U mod P is going to be equal to U. So this is a kind of a transformation that tells us that it is invertible. Even here I can claim that this actually is a one-to-one onto mapping, because U kind of like goes to V and then comes back to itself. And as such, it kind of disproves the invertibility of the mapping. But we could also do this. We could say that G that I just defined as a one-to-one and onto mapping from Z star P to Z star P. So to prove this, it suffices to show that in fact that the mapping is one-to-one. So let's just pick two numbers, U and V, that are mod P, and we just find their Montgomery pairs, GU and GV, and let's see exactly what happens. So we say that in fact they're equal. That means GU, which is UR mod P, is the same as VR mod P. That's equal to GV, of course. Now that means if I multiply both sides by R inverse, and that's why we had to have the inverse of R. That's why it's so critical to have that. If I don't have R inverse, then I can't really make this derivation or this transformation. But I can, because I know that R is invertible mod P, so I have R inverse. So put the R inverse on both sides, and they cancel out, and then I have U equal to V mod P. I began with two distinct positive integers, and I said, let's say actually they get mapped to the same place as I convert them, transform them into their Montgomery pairs. So if they're equal, if their pairs are equal, then they have to be equal themselves. So starting out with the assumption that they were two distinct integers, and then arriving at the fact that they are the same is a contradiction, so they must be the same, and they are. And so we can say that GU is one-to-one, that every integer in ZP, Z star P, is mapped to a distinct element in Z star P. And since the two sets are the same size, because we go from Z star P to Z star P, and everything goes to a different place, then the mapping must also be onto. So that really is the crux of this whole process. All we did, we took a set, and the set is 1, 2, 3, P minus 1, and then we transformed it back onto itself by this mapping, which we call G. And G is U times R mod P. That's all it is. Very simple. Okay? Now here's an example. If I pick my P equals 5 and R equals 8, I've got two numbers here, 1 through 4, and I'd like to see exactly where they go. So here's 1 times 8, mod 5 is equal to 3. 2 times 8, mod 5 is equal to 1. 3 times 8, mod 5 is equal to 4. And then 4 times 8, mod 5 is equal to 2. As you can see that 1, 2, 3, 4 here are mapped to 3, 1, 4, 2. They are all distinct, and it's onto map. This is what I was saying earlier. And this is true whatever R we pick, as long as we pick a prime. In this example, P is equal to 5, and that is a prime. So here's the Montgomery transformation. We start out with ZP star, and we take the direct product of the two of this ZP star, meaning that we're looking at pairs of numbers. The pair that we're interested in here, of course, is U comma V. That's our pair. We begin with a pair. We pick a number from ZP. We pick another number, which could actually be the same number. We pick that pair, which is this. And now Montgomery says, let's take those numbers to GU and GV, because that's the Montgomery pair of those two numbers, GU and GV. GV, or G of V. Now, so when you take G of U and G of V and multiply them in the transform domain, this is actually, we still went to the same place, because the transformation would put those two numbers right back into the same place. Not the same numbers, but some transform corresponding values. Like here, 1 went into 3 and 2 went into 1. So they got transformed back into the same place. So that's what this is saying. Now, all we have to do is to give an interpretation to the multiplication in the transform domain. This is the transform domain here. So we got our numbers GU and GV, G of U and G of V, but the multiplication now is defined not as the product of the two, but the product of the two times R inverse mod P. That is how we understand the multiplication of the two numbers. That number now is our multiplication, the product. And we want to know, when we take that number back into the original domain, whether that actually goes back to the product that we intended to get, which would be U times V. So on the way back to the original domain, we make this Z, which is this whole product, mod P, go back. And the go back means, of course, multiply this thing now, going back in this direction, multiplied by R inverse. And as we do, we get ourselves U times R, V times R, R inverse, R inverse. So R in here, R in there, R inverse in there, and now one more R inverse that comes about because of this transformation back to the original domain. We get ourselves a U times V mod P. If I could write this down here real quickly, it'll be somewhat a derivation that I will just simply quickly do here, right there, for example. What I'm saying is, just looking at this expression down here, G of U would have been U times R, G of V would have been V times R, and then of course we have R inverse. And then we are also going to do one more R inverse. That's actually going back to the original domain. That's how we get the second R inverse. Okay, and that will give you, and this is mod P. That's the same as U times V mod P. That's what we got. So that's what you have right there. Okay. That first R minus 1, R inverse, that is, comes about because of this introduction of that factor in this multiplication. And the second one comes about because we're going back, and going back means G inverse Z, and that means multiply Z by R inverse, and that's the second R inverse. So the two R inverses cancel with the two R's, and you get back to U times V. So this red line, the red path, instead of like going down this way, has given us what we wanted to accomplish. Of course, this is still a complicated process. As you look at it, we introduce lots of multiplications into this, and then, we may not be very optimistic that this will lead us to the place that we want it to be, which was to simplify all the mod P computations. And all of a sudden now we see that we made a lot of other factors come into our products, and would this really help us do anything useful? Of course, when you know what you're doing, as Montgomery did when he did it, you don't really have a problem. This is what I just explained to you, so let's just pass over this. I was just saying that on this side, the vertical edge down gives us this. UV goes to U times V times mod P. And the red path that I showed you would have done this, basically. And I didn't realize, I just had forgotten that I had written this down, so you can see that that these will actually cancel, and I did this in 2 steps. This is the inverse process. This was actually the multiplication plus this extra inverse that we introduced to our definition right there. So here's an example. If I pick my p equal to 53 and r to 64, and then I pick 2 numbers, 18 and 25, then first thing that I want to compute the inverse of r in mod 53. I'll show you how to do this in just a little bit, but for right now, assume that I discovered this already, and I figured that 29 is the inverse of 64 mod 53, which this is. That the difference of this product and this product is equal to 1. That's how we get that number 29 to be the inverse of 64. If I make that assumption, then the map that I just described does this. It takes 18 and 25, which happen to be our u and v, and then map them to g of 18 and g of 25, which would be multiplication of 18 by r, which is actually equal to 64, and modding it to 53, and then same is true for 25. So I get to go to these 2 numbers, 39 and 10. Now I want to multiply these 2 numbers in the transform domain, which I do, but I also have to multiply the 2 by the inverse of r, which is equal to 29. That's how I define the multiplication, if you remember. That has to be in there. So now I do this, and I mod it to 53, I get 21. So it's this number that I got to go back to see if it actually matches the product of u and v, 18 times 25 mod 53, which happens to be 26. I want to know if I get back at this number by coming back from here. So that 21 now has to be transformed back into here. And the way I do that is this time I take r inverse and multiply it by that number z, which is this number here, and then mod it to 53, and that is equal to 26. So what exactly this shows is that if I had gone along the red path, I would have gotten a 26. If I had come down this way, I would have gotten a 26. Well, you're looking at this and saying that, why did we not do this? We just multiply the 2 numbers and mod them to 53 and we get a 26. What was this extra process all about? Well, remember that the thing that we wanted to avoid was not to make this mod 53 reduction, because this would require the division that I talked about. This product must be now modded to 53, meaning that I got to do a long division. Well, of course, I also did all of those things in here, right? Here, to compute this, I had to do 21 times 29 and mod it to 53. Well, that's a lot of, steps, the same as this. In fact, not only that, but also I had to do this one more time here. Not only that, I had to compute it over here. I had to compute this 18 times 64 mod 53. I had to compute this to get those numbers. And I had to do all this stuff one more time. So how many times I've done that? 1, 2, 3, 4 times. I had to do one of these here. I ended up doing 4 of them there. So what is the advantage? Why would someone actually even bother to go along this direction? So that's the thing. That's, what sometimes people with, foresight do. They go along a hill, a ramp, and they somehow have the vision to see that long or apparently or seemingly long path is actually not that long at all. So now Montgomery is going to convert these very tedious processes. If I had only done one, I would have been basically even with this process. I've got 4 of them in here. 1, 2, 3, 1, 2, 3, 4. So I have to justify, 3 extra steps to break more than even on this side of the transformation. Well, that's exactly what he does. So this again is what I just said. We need to have an efficient process, and that's what he does. That's what Montgomery does. Let's assume that this x that I've written down here is the product of u and v. That's I now computed u times v, and I am looking at at a process where I want to get this whole thing computed in Montgomery domain. And that means I need to do, like u times r mod p, and I need to do, v times mod P, V times R mod P, and so on. And on the actual transform domain, I got to do these, the pairs that I call GU and GV, and I have to multiply them by R inverse and then mod that to P. And on the way back, whatever number I get there, which I call Z in this map here, that Z must now be multiplied, in the reverse direction to get back in here. So what Montgomery did, he defined two numbers. Look at those two numbers now, M and T. And look at the things that he does here. Something modded to R. By the way, X is R, let's say. We could assume that it's actually U times V. It's just some number which could go up to P times R. We're doing things, like mod P. But X itself, when you multiply two numbers, it can go up to P squared, really, no more than. But that's clearly less than or equal to P times R, because R itself is greater than P. So he says, I can actually take that number X and then, perform this operation. And in the process of performing this operation, you notice that the only thing that he does, he takes that X and he mods it to R. So it's a mod R, but R is a power of 2, if you recall. Right up here. R is a power of 2. So let's go over here again. I take a number, mod it to a power of 2. What does that mean? Truncate it to the rightmost k bits, because R is 2 to the k. And then multiply it by Z and mod it to R again. What does that mean? Well, that means that I'm going to truncate it to the rightmost k bits. Forget about the leftmost, whatever number of bits I have. After this multiplication, I can have more bits, but I forget about them. I only look at the rightmost k bits. That's truncation. How about T? A T is like M, that number, whatever that is. I computed it only by truncating whatever bits I got by way of these multiplications, like that one, and maybe the original number could have had more than k bits. When I multiply U and V, for example, I could arrive at such a number, because U and V would be some two numbers between 2 to the k minus 1 and 2 to the k. And then T itself is X, that original number I had, plus M times P over R. What does it mean to say over R? That means shifted by k bits to the right. So that's a shift of bits, this one is. And that's a truncation. 2 truncations and 1 shift, k bits. And 2 k truncations and 2 k bits. I've got myself 2 numbers. But what are those 2 numbers? And how are they related to this X and its Montgomery pair? Because we got to get those pairs all the time in place to be able to compute, to make this computation. I always have to do these GU business, GV business, and so on. They all involve this multiplication of U or V by R and then mod it to P. Same thing over here. R inverse that time. So he actually established that this T is none other than X times R inverse mod P. And not only that, it is actually an integer, this whole number is. That when you make this division, you don't get some kind of a number which you then have to floor. This itself is an integer. There's no residue, there's no fraction left in the division. There's no flooring required. So here we go. T is equal to X plus MP over R. That means T times R is actually equal to X times X plus MR. I'm just sorry, I just have to make a small correction in here. Let me just do that. MP. Okay. TR is equal to X plus MP. Okay. Continue from that. Or we could say that TR minus X is equal to MP. What exactly does this mean in the context of congruences? That TR and minus X, or rather X, are congruent because their difference is a multiple of P. That means they are the same number when we think of them as mod P. If they are the same number, and when we think of them as p, and since r is actually has an inverse mod p, I can multiply both sides of this by r minus 1, which I do here. And when I do, r and r minus 1 cancel out. And I get myself x times r minus 1 mod p. So look what happened. The t that I just computed happens to be just what I actually wanted to have. Actually, I wanted to have x times r mod p, but I'll show you in just a second that if I actually had x times r inverse mod p, I could also get x times r mod p just as easily. But I also need this. If you go back to this diagram right here, in this transformation here, I really have to multiply z by r inverse and mod it to p. I need this as well. But in the forward direction, I will multiply u by r and then mod it to p. And then I do that also for v. And then in those cases, I need really r to be there, not r inverse. In this case, I need the r inverse also. So two r inverses and two r's multiplying. But now my formula here, that so-called t, which I have written down here, happens to be this number. For my x, that is really I call this the inverse Montgomery pair of x mod p. That's what I've got. Now, what I'm going to show you now, that t is actually an integer. Because if it's not an integer, I'm kind of fried. I will have to make it an integer. So how do I do that? Well, so m itself is x times z mod r. Where does this come from? It comes from here. So I'm going to push this back here. That doesn't matter because I have to take this mod r anyway. So I'm going to continue multiplying. Let's see. This mod here is just pushed over here. So what is left is x times z. Just move this out of there, put it there. So you get x times z mod r. This is what exactly I have here. But with the x times z mod r being the same as m times p must be equal to this. I just multiply both sides by p, and that's what I get. All right, now I see this at pz, and I have this formula, because remember that, r had an inverse with respect to mod p. So that means this inverse times r minus pz is equal to 1. That gives me the opportunity to actually take this pz out of here and compute it as r times r inverse minus 1, which I do. And then I make that pz, bring that pz into here, and I substitute it in there. So xpz now has become x times this. This is equal to r times r minus 1 minus 1. That's what pz is equal to from this equation. So I put it in there. That comes right from there. X times pz, x times whatever pz is, which is equal to that minus 1, which I have inserted in here. Okay. Now that I go to basically the simplification, what this is now telling me is that if I think of r times r minus 1 inverse, that is time x and mod r, that drops out. There's nothing's left on there because whatever this quantity is, it's a multiple of r. That means in mod r that doesn't exist. So that goes away. And what is left is minus x. So MP must be congruent to minus x mod r. That's what that means. I should probably insert it in there somewhere. It's all in mod r. Let me just do that maybe so that you feel comfortable. Put the parentheses so we know exactly how we interpret that. Okay, mod r. Because I dropped this out. Why? It's a multiple of r. This has to go away. What's left is minus 1 times x, which is what this is, and that means they are actually congruent. So if they're congruent, that means there is actually, I could have just surmised it directly from what I just said, but that's the same as saying this. MP plus x is equal to some k times r. Or t, which is obviously from this line here, is equal to MP plus x over r is equal to k. Because if I take this whole thing and divide it by r, what survives on the right-hand side is k. But k itself has to be an integer because that's how we define this. That the sum of the two, That is, this minus x, which means MP plus x, is some multiple of KR. That's how we define congruence. Or straight out of here, you could say the same. MP plus 1 is some multiple of R. So the conclusion is that this t that I computed is actually an integer. That had to be an integer for me to make this conclusion. So I now showed myself, or showed, I guess, you too, that t is not only x times r inverse mod p, which it is, but also it's an integer. But guess what? To compute t, or to compute m, the only thing I did was mod to r, or divide by r. Mod to r, or divide by r. Both these numbers were gotten only by those operations, both of which are straightforward in binary. One is truncation, one is shift. Okay, division by a power of 2. So now we just finished that, and moreover, we could sort of easily see that t is less than 2p, since when we look at t here, x is a number between, let's say, it could be as big as p squared. That would be like as big as, r squared if you like. But r is going to be divided by r squared, so r would survive in here at most. And then of course here, p is itself less than r. So, and then m would be less than p. So you can have at most p in here. And I would say at most really p here too. So the whole thing will be less than 2p. And now this really gives us what we want. Here is the actual computation of the transformation. I want to compute this. To compute this, I just take m and set it equal to this, and I take t and make it equal to this. If t is greater or equal to p, return t minus p, else return t. I think in the text lecture notes I wrote this as p minus t, so I stand corrected, and it has to be t minus p, in case that you're wondering. So here's an example. My r is equal to 16, my p is 11. Clearly, this is a number between 8 and 16, 2 powers of 2. And I compute my r inverse to be 9. You can actually see that's the case by this equation, and z is equal to 13. So if I multiply 16 by 9, which is the inverse of 16 in mod 11, and then multiply 11 itself by 13, the difference is actually equal to 1. That's how I conclude this to be the inverse of 16. And now to compute the inverse Montgomery pair of x, which I set it to 150. That's just an example. You could pick any other number you like. I just go to work. I take 150, I mod it to 16, multiply it by 13, mod it to 16. I get these numbers. You can compute them easily. I get a 14. And now to go to t, from there, I take that x, put it in, multiply, add to it m times p, which is what I'm doing here, divided by 16. That's 19. That's actually greater than 11, so I make the correction. That's equal to 8. In binary, I do the same. Here's my number, 150. Dividing it by, or modding it to 16 means that I'm only going to look at the rightmost 4 bits. That's what this is. And now I have to multiply it by 13, which I'm actually going to do, and then mod it to 16. That means I'm going to look at the rightmost 4 bits, which I do. That's what I get. So that's a truncation, basically. That was my m. I got that, that result, which is equal to 14 here, just by truncation. And now to go and compute t, I do this computation, which is basically x 150 plus m times p, which I do in binary. I got to do this divided by 16. So I do the multiplication, insert it in here, add the two together, and now that I've done this, I'm going to shift it by 4 bits to the right. That means those 4 zeros will disappear. What is left is going to be this, and then of course that is the 19 that we were looking for. And then I do the correction by mod subtraction, and I get myself 8, which is what I wanted to have. To check that this is really what I wanted to have, which happens to be x times r inverse mod p, which is 11, I go out and do it. think I just copied. I did this 2 times, so never mind this. Actually, I don't need this, so let me just, I think I'm doing the same thing one more time. Let me just delete this. This is the same as this. Yep. I'll just delete that. How about that? So now we are back at the correction step, or the check step. So I'm just trying to check if, in fact, what I've got is correct. So I'm asking the t that I just computed over here, this t, which happens to be 8. Is that really the same as x times r inverse mod 11? Or I'm asking, is 8 congruent to 150, which this is, times inverse of r, which is equal to 9 from this formula here? Are they actually congruent to one another, mod 11? That means that that times minus 8. Is that really congruent to 11? The answer is yes, because what this gives me is, I guess, 1432, and that's equal to 122 mod 11. So that checks, basically. I computed t, which is this number, which is mod p here. I computed all of that only by truncation and shift. The correction step is there because that 19 turned out to be greater than 11. If it's not greater than 11, then we would have not required that correction. But the correction is only one subtraction in this situation. That's all it is. Why do I say only one? It's really critical. You have to emphasize that. I have to emphasize it myself because what did I say here? The t is no more than 2p. Therefore, the correction amount is restricted by no more than one subtraction. All right. So now this formula gave me some number times r inverse mod p, right? We actually figured this out earlier. We said that t is x times r inverse mod p. But what I'm really after here is that I want to do this because in my original transformation I did have a requirement like this. Here I have to go back, and then in going back I have to multiply z by r inverse and mod it to p here. And also here I have to do this r inverse mod p, but in going forward I need to multiply u by r and mod it to p. So I take care of that and this step, but I haven't quite taken care of this step. So this is how it is done here. Okay. If I want to do u times r mod p, but not u r inverse mod p, then I think of that u times r mod p as u times r inverse r squared mod p. They are the same. Okay, I end up having r here. So that is now simplified to this. I bring the r square inside the parentheses here and then take the mod p of it. And then whatever number that is, I multiply that by u, and then I multiply that by r inverse and mod it to p, and effectively this now is equal to this. So to do the left-hand side, I do the right-hand side. The right-hand side I know how to do. Why so? Because here's my r minus 1. I just actually define m and t, which will give me this product by r minus 1. But I've complicated my process only a tiny bit, not really much. One extra multiplication is all I have to do. And look at this number. This is a constant. Why is it a constant? Because my r is fixed, my p is fixed, so this will always come out to be the same, no matter what u I pick and what transformation that I'm interested in. So u certainly is a variable because I want to multiply, let's say, any two numbers mod p. But r, by that time, is fixed to be that power of 2 that is just greater than p. And r squared is a constant because r is a constant. And the mod p of it is a constant. So whatever this number is, it's like a coefficient. I've actually sort of equated this transformation, I call this the forward transformation, to this transformation, which looks like backward transformation, but I have a little bit of a coefficient that must always multiply u. And that coefficient is fixed. That's done offline. I actually compute that, and whatever number it is, anytime I want to do this transformation here, all I have to do is to take u and multiply it by that, and then multiply everything by r inverse and mod it to p. I would have effectively computed this quantity by doing this. One more time. This is a constant. R is fixed, P is fixed. And therefore, that fixed number times U is some number mod P, but that extra multiplication is just fine because I'm actually not doing any correction there. I'm performing a multiplication. So the inverse direction is straightforward because that is actually directly U times R inverse mod P. No need to do anything here, but going forward, I have these two extra multiplications that I have to perform, one for U and one for V. That's why I say two extra computations. So I guess you can say that there is a trade-off in here. And what is it? We are just replacing one long division by two multiplications. Multiplications being U times this quantity, and then V times this quantity, if I'm actually interested in doing U times V computation in the transform domain. Now, mod addition and subtraction can be done just as easily because if you think about the transformation that we generate, U goes to U times R mod P, V goes to V times R mod P, and now U times R mod P plus V times R mod P, this is the transform domain, is the same as U plus minus V mod times R mod P, just equal, this is equal by definition. And if I want to go back, I multiply this thing by R inverse alone. That will then take care of the R. I'm back to what I started out with. So to do addition, I transform U and V to those two numbers, mod P, and I've just shown you how to do this in the Montgomery by the Montgomery algorithm, okay? And add the two numbers up in the transform domain, and to get back, multiply it by R inverse. Now these are all done by truncations and shifts. Now you may say in this case that you can argue, and I think I would accept that argument, that this multiplication and that multiplication right there, mod P, in both cases, involve an actual multiplication because these are the forward multiplications we talked about that actually requires this sort of a multiplication in here. And those two steps are extra because all we wanted to do was to add those two numbers. So this is not so much that you want to carry your computations in the transform domain, but technically you can do this and you're not going to harm yourself doing this, except it won't be efficient. So you can carry out those computations that are additions and subtractions in the original domain. You don't need to go to the transform domain, but whenever you do a multiplication, to avoid division, long division, you can actually go ahead and do this. So again, these are just this particular slide is referring to the fact that addition and subtraction remains intact when you make the transformation, but you don't really have to do this because it will ultimately introduce these two multiplications in the process, which you didn't have to do if you just did a straightforward addition on the original inside the original domain. So I guess the short end of it is addition and subtraction wise, a Montgomery algorithm doesn't pay at all, but multiplication it does. It replaces two multiplication operations or one long division operation by two multiplication operations. I guess this slide is a little bit too crowded for me even, but the idea, the essence of it is that if I take some formula in the original domain, and that's maybe where the utility of the plus minus, or the plus in this case comes up, I can take it and I can actually create what's called an equivalent Montgomery formula for it. And to do so, every time I multiply, I actually introduce the R's in the forward direction. R inverse comes in the transform domain. Because I'm multiplying, that means I got to put that inverse. And again, here, W and X, they have to be transformed, as you see that they are. And the inverse comes in because I'm multiplying them. And then I have to multiply the whole thing by Y plus Z. That's where that R inverse comes from. But the transform of these would be just YR plus ZR. And that's the whole, a step. And then now, in order to actually get these forward transformations simplified into the Montgomery algorithm, then I have to introduce R square mod P R inverse, and I get to introduce those. By the time I finish this, everything is actually now in the Montgomery domain. Not that I have to do the addition and subtraction in this fashion, but I now create an equivalence between the original expression and the transform domain, which is Montgomery domain, which is our Montgomery domain. And then now I'm going back. So this is just like going back from here to here. I basically do everything in reverse to get back at here. I'll leave it to you to actually peruse through this inverse process to convince yourself that what we began with is what we ended up having here if I go backward. This is going forward, this is going backward. Okay. Now the only thing that remains is division. Division, of course, also involves, when you compute the residue, since it actually it amounts to multiplication of a number by the inverse of the second number that your divisor, that would still involve a long division, because when you want to compute the mod p. So here we go, and like I define the inverse of, or not inverse, but the Montgomery pair of a number, like a V inverse, as basically that number times R. Nothing unusual here. That's how it is defined anyway. This is just a number, I multiply it by R, and that is the dual, the pair of V inverse in the Montgomery domain. So that means if I were to divide U by V, I just have to multiply U by the inverse of V, and of course that exists because P is a prime. And the transform itself is given by this. Now, so that's what I do. I take those two numbers and move them into G of U and G of V inverse. And now I got those numbers in there. I have to multiply everything by R inverse. That hasn't changed because it's the same multiplication process I'm actually performing. I get those numbers in there. Now I got to go back, meaning that I have to multiply this whole thing by R inverse. The two R inverses would cancel to the two R's that I introduced by way of these G's that I have in here. So in the end, I'm going to have myself U times V inverse, what I intended to do here anyway. So here's how that is really explained. From here to there, and from there to there, you can see those R inverses will only, the R inverse will only cancel one of these, but then I have to introduce the second R inverse, which I actually do here. Let's see. So here we go. G of U is basically U times R, V inverse times R, and then R inverse comes from here. So that will cancel with this, and I get that. And of course this, by way of this transformation, going back, will have to be multiplied by R inverse. That will take that R out of there, out of the way, and that's what I've got here. And that's the same as like dividing U by V mod P. So that's very nice. We can do division just as easily. The only thing, of course, that now remains is, how do I do the inverse of V? That's the only thing that remains. I still have to deal with the issue of inverting a number mod P. So we've kind of elevated ourselves to a place where multiplication and division are easy, but inverse is still, that remains to be handled. So there are really two algorithms in mod P that can take care of the inverse computation for us. One is the ancient Euclidean algorithm, and they actually extend it to what's called extended Euclid algorithm, and the other one is Euler's theorem. I'm just going to show you both of those. So if you're doing basically Euclid simply tells you that you can actually carry out modulo division, or you can compute the inverses by way of Euclid algorithm, which simplifies the greatest common divisor of two numbers. That's what Euclid algorithm does. You give it two numbers, it then computes you the greatest common divisor. Now, if I pick myself a prime modulus, and I want to find the inverse of a number in that modulus, then I just go out and compute the greatest common divisor of the two numbers. Now, since prime, the modulus is a prime, no matter what number you pick, the greatest common divisor will have to be equal to 1. Okay? And that's critical, because if that's the case, then we could use this greatest common divisor algorithm to actually find out an expression of the form which I've actually listed down here. Because ultimately something will be equal to 1 in here. Like, in fact, let me just go this process step by step. When we start out with two numbers, like, in this case, 37 and 20, we will ultimately get it down to, in this GCD greatest common divisor process, to an equation where actually something would be equal to 1, and from there we can go back, and that's called back substitution in the second phase, to really find out what the two numbers that we're interested in would be. And then, in fact, it'll be in this form, as you will see in just a second. If you can sort of convert this GCD, greatest common divisor process, to this form, we know what our U inverse is, which actually is this, and what this other number Z is. Okay, so here's how we begin. We take, for example, 37, and then we write that as, we divide 37 basically by 20, and that gives us a remainder, which then goes into another step. Then we take 20 and then divide it by 17. We get to 3. And then we take 17 and 3 together, and we get 2. And we take 3 and 2 together, and we get this. So this is where the last remainder we find out here, which will be obviously something that is actually going to be less than or equal to the last divisor we have. Okay? And that will always be equal to 1. That's when we stop, which in this case happens to be the situation. So here we still have to divide, because what we really have as a remainder here is greater than this. So we keep dividing until we get to a point where we either get 1 or something that's less than this. So this formula right there tells us that we can always arrive at an equation where the last term will be 1, because this is the greatest common divisor of the two numbers that we were trying to find the greatest common divisor for. That happens to be 1. So now we take that last equation and write it in this fashion, if you notice. So 1 is equal to some number minus 1 times 2. Well, all we have to do is now take this 2 and replace it by whatever 2 works out to from this equation prior, which is 17 minus 5 times 13, 3, I'm sorry, which we actually go ahead and do. We replace this by this. All the while, 1 remains on the left-hand side. It never really changes, as you notice. And by the time we finish this, we now have 6 times 3 minus 1 times 17. So we now have to replace 3 by whatever this equation reveals. In the end, you will see that 37 and 20 will be the only numbers that will survive this process. So let's go ahead one more time. Replace that 3 by this, 20 minus 1 times 17, which we do. And we just multiply it out. Now we have 6 times 20 minus 7 times 17. And take the 17 out of here. And then replace it by 37 minus 1 times 20. Okay? And then when we do this, take it out and put it in here. 37 minus 1 times 20. And you now notice that the only numbers that we really have left are 37 and 20. We get this nice equation. And if you look at this, we got our number 20. We got our number 37. Those are the two numbers that we wanted to work. We were just trying to compute the inverse of 20 in mod 37. And we put it into a form. And they are actually equal to 1. So this is our prime modulus multiplied by some constant like z over here. And when we subtract that quantity from some product in which one of the operands happens to be 20, which is actually the number that for which we want to find the inverse, that will be our u here, as you can see, multiplied by some other number, and that has to be u inverse. So this tells us 13 is the inverse of u. So that's that process. So how does it work? We take the Euclid algorithm, we go down this way, phase 1, and then the other direction, we actually go backward by simply isolating in consecutive manner, all the remainders have to be back substituted. And as we do it here, we put the 1 on the left-hand side and never change the side of the equation. And these red painted digits, or the numbers, are the ones that we actually keep substituting. 2 can be substituted in here because there's a formula. Once we do, 2 disappears, only 5 and 17 remains. 3 and 17 remains. And then now we can replace 3. Only 20 and 17 remain. And then now we can replace 17, and only 20 and 37 remain. And that's what ultimately is what we need to have, because we got to get to 37 and 20, and somehow 2 numbers multiplying them, and that must be equal to 1. with a minus sign in front of it. Now, at times, we talked about this first part, which is basically because we have a prime number, greatest common divisor of that number with any other number has to be 1. But in the second part of this slide, I'm just talking about something that's kind of critical to note. In certain cases, I haven't really sort of formed an example for this. We may actually have an expression that that may be in flip form. The flip form meaning that instead of having the p times z term with a negative sign in front of it, we could actually have it with a positive sign. So if you look back here, we want this term to have a negative term, a minus term, minus in front of it. But it could be that you could have this formulation. When this happens, and you want to put it into this form, you have to do a little correction. You would take this expression, flip form, and you will then add and subtract from this u times p, as I've actually indicated here, right there. So you will add once and subtract once, subtract once and add once, the same term. That means that you haven't changed anything. Once you've done that, you can now regroup things. And that is, you can take now p, factor it out to this form. So z2 minus u is what survives. And then you take the second one and then actually factor the u out, and you get, u times p minus v2. Okay. And then I want you to write this, or let's just say that you could do this. You put this term on the left. You know that p minus v2 is always going to be positive because p's the modulus and v2 is just a number between 1 and p minus 1. So this is always greater or equal to 0, and I copy it over. But then I write this as minus p times u minus z2. And then I claim that if this were to be equal to 2, equal to 1, then this quantity must be positive. Because if it's negative, and this actually is positive, we know, and we have two numbers here, both of which are integers, and we add them up, let's say this turns out to be negative, another negative in there would make this whole quantity positive. That whole quantity being positive, added to another positive quantity, both of which are integers, would never be equal to 1. So therefore, you have to say that this must be positive. So that u minus z2 must be positive, which is kind of nice. That's exactly the form we want in here. We want that z1 to be positive. So now, because of that, we actually set our z1 to u minus z2, and our v1 to p minus v2, and that will just get you the two numbers that you're interested in, namely the inverse of u, which is equal to v1, and z1 itself, which is the factor that multiplies p. Okay, so that's Euclid algorithm. Now, there's also a possibility of using what's called Euler's theorem, which simply goes like this: if you actually have a prime number p, then actually, before we even get to that, we can even say this. If you take any number between 1 and p minus 1, that's our u in this case, and then if you power that, that's a very, very powerful statement, I guess I should also say, by Euler. If you power that, and the proof of which is not that straightforward, but there is a proof. If you power this by what's called the totient function of p, which is the number of numbers that are relatively prime to p, and p doesn't have to be a prime for this to hold, then it's congruent to 1, mod p. If, on the other hand, or in addition to this theorem, p is a prime, then the number of numbers that actually are relatively prime to p would have to be p minus 1. Okay? That's the number of, if you take any number, prime number p, and then count the number of numbers that are actually relatively prime, that will have to be, that is the greatest common divisor being actually equal to 1, then there are p minus 1 such numbers between, I guess, 1 and p minus 1. And so that tells us that just replacing this by p minus 1, we get ourselves this formula. Okay. After we multiply, of course, this by u. But now this totient function psi of p is equal to p minus 1, and therefore we get this. Okay. So what exactly is this saying? If you want to compute u inverse, all you have to do is to compute u p minus 2. That's all you have to do. So you can always get at the inverse of u by powering u p minus 2 times. So how do we do this? We actually use what's called repeated squaring, which is like this. So you set s to p minus 2, and then initialize v to 1, and then t to u. And then while s is greater than 0, you're going to continue to do this. If you find that s is an odd number, you're going to multiply v by t and mod it to p. And if it's actually, that's the case, you do this only then. And then regardless of whether it's odd or even, you always multiply t by t, and then you replace t by that. So this is not part of the if statement. This is always done in each iteration. And of course you divide s by 2, meaning like you try to bring it to 0. When this becomes 1, of course, you will stop, because it says as long as it's greater than 0 you have to do this, and you divide 1 by 2 again, you get a 0 the next time, so you quit when that happens. So here's the example, P29, and you want to compute, U27 powered, U raised to 27, and to compute this you begin with 27, you set it to that, and then initially of course this was equal to 1, and now t is equal to u, and then at the end of the first iteration, you simply set v to 1 times t, which is equal to u, which is what this is, and then t squared, t is u squared, which is what this is. And you keep doing this down, all the way down to when s is equal to 1, at which time your v u to the 27 mod 29 is computed. I guess the best way to think about this is what's called an iterative version of a recursive algorithm. It's actually called, this whole thing is called recursive doubling, because what you want to do is to start out at this number 27, and then you want to find the highest power of 2 in there. In other words, you want to divide this into 2 portions. One is the highest power of 2, and then that added to the next, the other remaining numbers. So 27 is 16 plus 11. And you do this, you apply the same algorithm to this node now. So in other words, what is the highest power of 2 that will be contained in 11? And that's 8. And so you want to get to 27, you find the highest power of 2, and then add it to what is left. And then you haven't quite parsed this vertex yet, so you apply the same algorithm, and then it gives you 8, and then what's left is 3. Now apply the same algorithm. So you can see that you can get at 27 by adding 16 to 11, and of course 11 can be gotten by 8 and 3, and then 3 can be gotten by 2 and 1. So it's really a decomposition of 27 into powers of 2 is what this is, ultimately. 1 plus 2 plus 8 plus 16 is 27. And you kind of compute this by this process of recursive doubling, 1, 2, 4, which you never get to use because 11 never breaks down that way, and then you kind of go back up to 27. So this algorithm is fine, but how do we use our Montgomery algorithm for this? Well, we could do this if we just realize the fact that all these steps that we put in place here can be done in the Montgomery domain. So I can take, for example, V, create the Montgomery pair of it, and the same way T, and same over here. So all these things can be done, mod P computations, by way of that power of 2, which we call R. Okay. So you can see that we still get the inverse, but now I'd first translate the initial number, which was equal to 1, to its Montgomery pair. So what is the Montgomery pair of 1? It's 1 times R mod P. How about T? I call this Vm because that's for Montgomery, and that's Montgomery M. And of course it was equal to U, that T was initially here equal to U, right there. So now it's going to be U times R mod P. And of course I can do that by way of this constant times U computation and then R inverse. And this is exactly how I know how to do in Montgomery itself. And then the same loop remains. So now what was the loop itself? We'll always do this computation. Always do this computation and do this when if S is actually odd. And that's what I'm doing here. I'm doing the computation of Vm, which is the product of Vm times Tm, R inverse. And this one is always done. That is squaring T, but that means squaring Tm. So same algorithm, numbers, the operands have been translated into Montgomery. Okay, so that's really it. Now I can use the same process one more time, and this is really what I done here. I took my P to be 29, and I picked my R to be 32, that is 2 to the 5. I computed R inverse by way of the algorithm that I actually, this is done offline by the way. I only do this once because R is a fixed number. And if I were to, for example, find the inverse of, let's say, number 2, all I have to do is just apply recursive doubling or repeated squaring. But now the computation must be done in the Montgomery domain. This is really what I've done here. Until I get to a place where I find my VM to be. You notice that these mod operations here are not really done in mod 29, but done by way of these transformations, which will be all, these transformations actually will all take place by this very computation here. Right there. Where this X will be replaced by whatever transformation that I need to perform at that point. That is, sometimes actually VM and TM are initially conditioned, and then after that I have to do this every single time. So this is, for example, one such transformation where I'm actually doing a Montgomery pair for the product here. Whatever product I get must be Montgomery paired, and then the computation takes place from there. That multiplication has to be performed in that fashion. Now, and that's precisely what's happening here. And so in the end, I get this number 16, and that number, of course, will have an inverse, and I find that inverse to be, the way I find that, of course, is by multiplying it by R inverse and modding it to 29. But even that computation is done by way of Montgomery transformation, and when I do that, I get myself 15, which is really the inverse of 2 in mod 29. So effectively, I covered, I guess, the Montgomery algorithm, which showed us that multiplication can be converted into another domain to avoid long division. And we need 2 extra multiplications to really avoid division. And we also sort of saw that addition and subtraction, would not pay off to make those transformations. That we could still carry those out in the original domain. But the utility of this algorithm primarily remains effective for mod P multiplications when we have to perform them in binary systems. And I guess the second bullet says that if you just accept that fact, which obviously we laid out the reasons for, then your computations now reduce to truncation and shifts. And that really is the idea of this particular sort of lecture. And I hope that you've gotten bits and pieces of the ideas, if not all of it, all at once. Hopefully reading the lecture notes together with this particular sort of presentation will help you grasp these ideas a little more. I will put in one other maybe short lecture for, at least let me just say this, I'll try to do this for Diffie-Hellman and Rivest, Shamir and Adelman, so-called RSA algorithm, when I have the next opportunity to do this kind of a video recording. But now my task is to get this done and then actually email it to everybody as quickly as possible. So until the next lecture on video, everybody take care, and I'll see you when I get back to College Park by around November 10. Take care.